Okay, next up, we've got David Groves from Nominet, giving us a deep dive into the mechanics of timekeeping. Hi, David.
Yep, it is up. So this presentation is called Excuse Me, Do You Have the Time? And Richard Patterson, who's here, is to blame for that. I'm finding my clicker. Here we go. Perfect. It's not going to be quite as deep a dive as I could be because, ironically, I don't quite have enough time for that. But yeah, first question is, why does time synchronization matter? Matters for lots of different reasons to lots of different people. Two that have particularly affected me in my professional career have been log accuracy, telemetry, knowing what came first, what's the cause, what's the effect. Broadcast TV also uses it, which I've had a tangential involvement in the past as well. Stock market and HFT, obviously, not really my thing, and optimistic concurrency in databases. This was a use case that I had where we were trying to reduce the database load by doing some magic database tricks that I don't really understand, but I was told if we had very accurate clocks, we could save lots of money. And as I'm sure everybody knows, that makes managers love you. So there are two kind of goals here, right? One is device-device synchronization. You want two devices to have the same time. And the separate problem, but usually you want to do both at the same time, is wall clock accuracy. Does my clock agree with what the world considers the time to be? UTC or local time or whatever you're trying to synchronize to. Hopefully UTC. When we come to clock movement, there's kind of two main ways that we do this. There's stepping a clock, which is just like your microwave. You've had a power cut, you come back on, you want to set the clock to the right time. You just set it to the right time. Easy. And slewing a clock where the clock's wrong, but you don't want to jump it, and we'll see some reasons why you don't want to jump it in a second. So you change how long a second is, basically. You drag out time a little bit, or you shorten time a little bit to nudge the clock towards the right time, so you don't have those jumps in time, which obviously can be a problem. And I've got a bit of a comedy example for how it can be a problem next. Which is people that play video games. So people play video games and try and complete a game as fast as possible. People try and complete Mario Odyssey as fast as possible. This is a game came out on the Switch some time ago. I don't really know. And they do a trick where they set the game up just before daylight saving time transitions. So you've got the problem here of a stepped clock. You've got a problem here of daylight savings time. Agreements, and they use this to make a plant grow really quickly and complete the game faster, the details of which aren't terribly important. But it just shows how if you don't think a little bit about time, you can get these kind of crazy stuff going wrong on you. So how do we solve time synchronization? Probably everybody in this room has heard of NTP, and probably everybody's used it. This is the traditional way of solving these things, invented in 1985. By David Mills. I've got some fun stories about how when it first came to the UK to share. But this is network time protocol designed to synchronize clocks. NTP4 is commonly the version we use now. You might find a little bit of NTP3 out there, but anything else, hopefully not. How does it work? Well, it works a bit like this. This is a diagram that kind of shows you. You have a client at the bottom, which thinks it knows the time. And it makes a packet up with what it thinks the time is in, which we call T1. It sends it to a server. This is a slightly simplified view. I can't go into all the different modes NTP has in the time I have. But then that time gets received. When it arrives, the computer receiving it says what it thinks is the time in and adds it to the packet. So the packet now has two times in it. At T3 is when the server responds. So the server's got to do some processing, right? It's got to figure out what's going on. So T2 and T3 are usually not that far apart, but they are a little bit far apart. And it returns it to T4. T4 gets not really added to the packet, but added to the data when the client receives the thing back. And we can do some maths that I've pointed out at the top here to calculate two things. One is the round trip time, but that's like half of, so part of the problem here is we don't know we had the packets taking the same paths. The round trip time is, half the total time, but the one way we assume it's half of the time, but we don't know for sure. Which we'll get into how we can solve later with other technologies. But And we send a lot of these messages, right? And we use some stuff which I'll explain in a second on how it works. But this is the NTP packet. It looks like this. I've got a full breakdown of what every field in it is. I don't have time to go through every single one in immense detail, but there's stuff about leap seconds. They're annoying. Hopefully they're going, well, they are going away soon. There's a whole bunch of other stuff in here, including how much accuracy we've lost as we've moved through a chain of NTP servers, because each server has an idea of how accurate its clock thinks it is, and it adds we add all those dispersions together. So there's quite a lot of complicated stuff going on in here. And as I said, I've got time for a summary of the subject. So if you want to ask detail about any of this, come grab me at some point, or read the slides. You'll be able to get them later. Stratum's an important concept in NTP. Stratum 0 is outside the system completely. This could be a radio clock. It could be GPS. Those are the two normal sources that we're using for outside time. Stratum 1 is the first thing that speaks NTP in the system, usually an appliance or a server or network device. And then we go all the way down to Stratum 15. And this is effectively like a hop count for time, right? You've got your authoritative source of radio at the top, then the first thing that runs NTP, and then a hop count all the way down. If we get past 15, we're into special case where we don't know what's going on with time. Hopefully we end up down there. But usually 16 means something's gone wrong. In the packet, we had the idea of a reference ID. It's important to note when you're looking at this stuff that if you're looking at things and you see something in there that looks like rate or deny, it is a message that's put there. The stratum will always be 0, and there'll be this message in here telling you something is going on. Remember, stratum 0 there's no server at stratum 0, so stratum 0 in the packet is an indication that the packet has extra information in it about errors and stuff. Stratum 1 time sources, again, what's their reference source? It isn't part of the NTP system, so you're going to get a code there again, something like GPS or MSF for the UK radio time signal, and various other up to four letter ASCII codes telling you a external source, so usually radio sources and stuff like that. And Stratum 2 to 15, it's going to be the IP address of the upstream server or server, but it gets complicated. There's more than one. But ultimately, they are IP addresses, and IPv6 is a mess because it doesn't fit. The NTP timestamp format is really, really accurate. It counts the seconds since the NTP epoch, which is not the Unix epoch. It is the 1st of January, 1900. Interestingly, it is stored unsigned as opposed to signed, which means it's going to roll over in 2036, a couple of years before the 2038 32-bit Unix timestamp rollover. But it's very accurate. It goes down to 200 picoseconds or so, more accurate than anything I'm about to talk about can actually ever achieve. And we store it in 32 bits of how many seconds since 1970, and 32 bits of fractions of a second. As I said earlier, what happens, we're exchanging all of these messages, so I've just described what they are and how they work. But when a device is deciding what it should be doing with time, first of all, it looks at clock selection, which you can configure a client to talk to more than one server, so it's trying to pick out which ones are reliable. It does that by just looking at how consistent they are in their responses, how our packet's getting lost, et cetera, et cetera. Then we filter outliers completely, so although I might be talking to you and you're telling me the time, occasionally you just get it wrong, occasionally it's a bit further off than the rest, we throw those away. Then we weigh the samples that we've got as to which ones we think are on a trend and which ones aren't. The ones that are on a trend we weigh more heavily, we think they're more reliable. And finally, we decide what we're going to do, given all this information, which is going to be disciplining the local clock, nudging it slightly faster, slightly slower to get it on track. NTP is great when things are almost already correctly on time, and we're just keeping them there. It's not so great if you know the microwave situation. There's some type length value extensions to this, mostly used for security. We can sign NTP updates and stick the signatures on the end. There's a huge key exchange problem here. It's pre-shared keys. It's a bit similar to like DNS if you've ever had to deal with TSIG in DNS. You have to pre-share these keys. There's a new standard, it's like 5-6 years old, to do this with TLS to exchange those keys, but not widely adopted yet. That's the NTS network time security stuff at the end. So what causes stuff to go wrong in NTP? Well, one of it is that NTP is usually a user space program running on a server, or even a user space program running on a router. The kernel needs to time to process a packet arrives at an NTP server. The kernel needs to process the packet that arrived. On the client, the client needs to put the thing to the kernel packages it up into a NIC, plays it out the NIC, gets received into the server again. So there's all these little things going on. Now, if you're talking about trying to get time down to a millisecond or so, none of this matters. But as you'll see in a minute, these days often you want a lot better than a millisecond. So all of the time spent with the kernel messing around with stuff, not great. Also, network latency varies, right? We're network engineers mostly in this room. We know that things take variable amount of time to get through a buffer, how many packets are ahead of me in a queue. I can use quas to give NTP priority queuing, etc. But ultimately, there's still going to be some variance in how long it takes something to get through a network, particularly a big network with lots of devices involved. So that moves on to what the modern solutions are. PTP, Precision Time Protocol. It's a little bit of a newer thing. 2002 was the first version, although that version isn't in use anymore. 2008, PTP v2, that's the version we kind of care about. Updated a little bit in 2019 to 2.1. What's the key difference here? Well, the key difference here is NTP is a protocol that runs on the network. PTP is a protocol that runs and the network is actively involved in processing it. You need hardware. You can run NTP on any network, right? To run PTP, you need network equipment that supports it. Specifically, you need hardware timestamping. So when a packet is sent or received, you know exactly when that happened. And you need extra stuff. Now, this stuff used to be tricky to get, but a Raspberry Pi is now capable of doing it as a computer, for example. Although a common home switch won't. The support is coming, but you still need to know what you're doing. You still need to build a network around it if you want to use it. So in end-to-end mode, which is one of the two modes for PTP, messages get sent from some kind of master clock. We'll get into a little bit of that in a minute. A sync message comes out, and that has the time. It's just saying, I think this is the time. Every time that packet enters a switch or some other network device that is PTP aware, it logs at what time that packet or frame entered the device. It starts a residence time clock. And when it's about to play the packet out the other port, it knows how long that time was spent in the switch, and it adds it onto the packet as how long did I spend in residence in this switch. And it doesn't matter how many switches you go through, you're adding up all those residence times. So now we know how much time we're kind of spending in the network devices. In peer-to-peer mode, there's an extra piece of accuracy done here. We've got our sync messages, we're measuring our residence timers like in the middle here, but we're also exchanging peer delay messages constantly between all of the devices that are active in the network. So here you can see peer delays going back and forward between the device in the middle and peer delays going back and forward between the device at the end. So now, when that first sync message enters the middle router or middle switch, it can go, oh, I arrived on this port, and I've measured the delay between me and the switch that's at the other end of this wire to be, 30 nanoseconds or whatever it is. And I can I can start that timer. Instead of starting the residence timer at 0, I start the residence timer at 30 nanoseconds because I know it took 30 nanoseconds for that packet to come over the wire and get to me. So now we're not only measuring how long we spend in routers, we're measuring the link latency as well and adding all of this together. Slight aside to clock modes. There's a grandmaster clock. This is whatever in your PTP system. I am the boss. I know the time. There's an election process, which I'll explain in a minute, for how you figure out what that clock is. There are ordinary clocks, which are either master clocks or slave clocks. That is still the terminology used. There's a big debate. Not going to go into it. There's transparent clocks, which don't contain the time, but they're the switches that measure the residence timers. And there's boundary clocks, and I recommend you use those everywhere. Boundary clocks just are, I'm a clock on this side, I'm a clock on that side. You know, I talk to this person and I learn the time, and then when this person asks the time, I say. Again, a little bit of detail. Grandmaster clocks are elected like this. Big tip, priority 2 is the one you want to use, not priority 1. If you use priority 1, it is I'm always the best clock, even if I've lost access to my GPS feed or whatever, where I'm actually getting time from. Just put your priority, if you want to pick a clock to be the best clock, put it in priority 2. You can use either UDP or PTP for Ethernet, PTP over UDP or PTP directly over the Ethernet with just frames. Which one you want to use depends on what your equipment supports and what you're doing. For example, the audiovisual world is all about PTP over Ethernet, but other places PTP over UDP. You will note, the most observant of you will note in the PTP over Ethernet one that the peer-to-peer messages are in the same kind of reserved MAC address range as spanning tree, because we don't want that to cross anything other than the link, directly attached link. And there are different types of PTP messages. There's an announcement going, hey, I'm a clock and I want to start an election. There's the sync messages, which I've previously described. This is what I think the time is to get propagated through the network. Follow-ups are only useful if your device is a little bit older. This was the original way this worked. The time in the sync message couldn't be modified by the NIC. It could only be measured. So you would send the sync message, and when you received the sync message was the time, but you'd get a follow-up packet that contained what time the sync message was sent. Hopefully that makes sense. And then there's all the other different delay requests and peer delay requests and stuff going on. Again, don't have time to explain every single detail of PTP. That would probably be half a day or so. Timestamp format, we get down to 15 femtoseconds. It's ridiculous. You'll never need that level of precision. And good news, we won't overflow like Unix epoch and NTP epoch for 9 million years. So should be good. Hardware requirements, you need if you're running this on computers, you need computers with hardware timestamping capabilities on the NIC. As I said, used to be rare and expensive. Raspberry Pi 5 does it now. My random desktop I got that I didn't check whether it did it or not does it now. You know, it's getting better. And that's because the NIC needs this hardware timestamping and clocks close to the NIC. And you also need PTP-aware switching, routing, etc. equipment, which needs high-precision oscillator in them for keeping overall system time, and probably some oscillators spread out onto line cards, individual ports, depends on how the people manufacture the thing. And those things can cost like a few dollars each. So that's why, real commodity hardware isn't just adding this, because it does still have a real cost. Okay, if you want to build a P2P network, what can you do? One thing you can do is go buy something that'll do it for you, basically. These are Grandmaster kind of clocks designed to take feeds. The one at the top costs about $13,000. One at the bottom is about $4,000. They both basically do roughly the same thing. And you can take in time feeds from pulse per second sources or GPS sources. They have accurate oscillators in them to keep the time, and they'll distribute that time via P2P or NTP. But you can also build one yourself. You can use an appropriate server. This is what I did. You need to have a server you can put some PCI cards in. You attach an OCP time card. I'll show you what it is on the next slide, to an antenna. And you use some Linux software to set the clocks on the NIC, to what's on the time card, to what's on the server time. So there's software like PHT2sys and PTP for Linux that you configure and set it all up. Pretty easy. This is an OCP time card, thanks to the people at Meta who kind of put this idea together. It's a PCI card. It's got sources on the left, as you can see, for GPS time and radio signals to come into. It's got a rubidium atomic clock on it for keeping its time if it loses those things. And the card is about $300. The rubidium atomic clock's about $800. It's about $1,000 for one of these things, total, which is pretty good value, I think. You can use even more accurate atomic clocks on these if you want, but that's starting to get real money. And also, you have to worry about temperature control and a much more thing. Now, if you want to play around this at home, you might be like, oh yeah, $1,000 is a lot to play around at home. Good news is you can also use a Raspberry Pi 5, about 80 quid, and a GNS hat for the GPS signal. That's about 48 quid. You don't get the local oscillator, but to be honest, the timekeeping on modern CPUs is pretty good, including the ARM ones on the Raspberry Pi. Finally, there is SyncE. This is a synchronous Ethernet. Ethernet needs accurate timing of pulses, right? But doesn't need each end to be in sync with each other. SyncE tries to put each end in sync with each other. This is the final magic that you need to get extraordinarily accurate time, because now you know that both sides are sending at the same time, and you're kind of making sure that the round trip time is 2 times the one-way time, that no path is worse than the other, assuming that the routing is symmetric. Which, if you've got boundary clocks all the way, it will be, because it doesn't matter which path it takes, you're adding it up correctly. So here's a real-world example. This is the thing I put in. We had a data center with 4 spine Arista 7280 switches, 16 72 something, I don't actually know, leaf switches, and we had 208 servers in total connected, all at 40 gig. We ran this with each switch as a boundary clock, so each switch to a client, to a server, its master clock was the switch it was connected to. Its clock source master was the switch it was connected to. Then the leaf to the spines, that was another clocking relationship. And then the leaf to the spine to the time server we built, another clocking relationship. How did we test this? Once we built it and we thought we had time going well, we got some extra one of those OCP cards and we just shoved them into client computers. We hooked up the GPS feed into them and we went, does the time we're getting from GPS match the time we're getting from the network? How accurate is it? And it was this accurate. So unfortunately, the scale on this is a little tiny, but it's in nanoseconds, and the top of the scale is 50 nanoseconds, and the bottom is minus 50 nanoseconds, and the middle is 0 nanoseconds, right? So when we used the OCP time server, we got the red dots, which shows you that we were basically within about 3 or 4 nanoseconds of GPS time through our PTP SyncE system. The blue dots are when we were using the Raspberry Pi. As you can see, a little bit more variance there, but still within about 40 nanoseconds of the right time all the time, which, to be honest, for using a Raspberry Pi for this, I thought was pretty impressive. So what should you do? Well, what do you actually want, right? You probably don't need 5 nanosecond precision. Most places I've worked haven't needed 5 nanosecond precision. What's your budget? What you're going to buy? This is roughly what you could expect. I'm speeding up a bit, time. This is roughly what you could expect in terms of time, synchronization, using different choices. Finally, beware of hypervisors and time sinks. It breaks everything all the time. You can do it, but you've got to get it right. Don't just assume the defaults are going to work. If you're building a P2P network and you can make everything a boundary clock, do. Beware of leap seconds. They're a mess. Ask me about that later if you want. Monitoring it gets harder and harder the more precise you're going to be, because who watches the watchman, that kind of problem. There is NTP interleave mode, which is a bit like the sync and follow-up. NTP can, which improves the accuracy of NTP. I have a wider presentation of time. If you click that link, goes on about all kinds of other time problems. What do LINX offer? This I was asked to put in by Tim. 3 time servers, 2 in Telehouse North, 1 in digital reality. The 2 in Telehouse use GPS and the German time signal. The 1 in digital reality uses the UK time signal. They all 3 use GPS. This is a best availability service, but it's had 5 nines availability over the last few years. And if you think LINX could do something else for you in terms of time, and I have some ideas, Tim is open to being talked to about it. Finally, yeah, if you want the presentation, grab that. It'll be on the LINX website as usual. And I didn't get quite as much time to do that as I'd like, but I finished just about on time. So, yeah.